Just 1 minute as it's preparing. All right, so we are now live on our YouTube channel and our audience is filling up. So I'm going to go ahead and welcome everyone. You are participating in the 32nd annual Flagstaff Festival of Science, and we're so fortunate to have you here today, along with Ryan, our speaker. Just a couple of notes about the presentation today. If you look down at the bottom of your screen, you'll see a Q&A section there. Feel free as he's presenting, if you have questions arise that you want to ask him, go ahead and type them in there. You can also give a thumbs up to any questions you already see in there if it's one that you share and you want to get a vote in for it. After Ryan's presentation, we'll try to get in as many questions as we can at the end. And I'm going to go ahead and turn it over to Greg for Ryan's intro.
Okay, thanks, Virginia. It's a pleasure for me, as always, to introduce the next speaker, Dr. Ryan Anderson. Ryan's a research scientist at the USGS Astrogeology Science Center here in Flagstaff, Arizona, and a leading expert in planetary science, especially when it comes to the science of Mars. Ryan's been studying planetary science for more than a dozen years now. He's an expert in data processing, writing computer code, infrared spectroscopy, and geomorphology, the study of landforms. And he says he's having the most fun when he's zapping rocks on Mars with lasers to figure out what they're made of. Ryan's a science team member for the Curiosity rover that's been collecting data in Gale Crater for many years now, and also for the Perseverance rover that just landed in Jezero Crater earlier this year in February. Ryan's also a regular presenter for the Flagstaff Festival of Science after-school program, after-school talks. So thank you, Ryan, for coming back, and take it away.
All right, thanks, Greg. Let me get my presentation shared here. Okay, hopefully you can see that. And I'll get started. So yeah, today I'm going to be sharing a little bit about sort of the similarities between the Earth and Mars and how we can, quote unquote, read the rocks, how we look at geology on Mars and then match it up with geology that we see on Earth and use that to understand what's going on both planets. So if I can advance my slide. So you'll often hear people say that Mars is the most Earth-like planet. And that's true. Venus is actually closer in size. Venus is almost exactly the same size as Earth, where you can see in this picture, which is to scale. Mars is quite a bit smaller. But Venus is very different in many other ways. It has this runaway greenhouse effect, and it's boiling hot on the surface, and it has clouds of sulfuric acid. So despite being the same size, Venus is a very different place. Mars, on the other hand, is quite similar, despite being smaller. It has a roughly 24-hour day, which simplifies things a lot for us for Mars rover operations. It's similarly tilted on its axis, so it has similar seasons, 4 seasons. It has polar ice caps, it has weather. It doesn't have big rainstorms like we do anymore, but it does have weather and clouds and wind blowing around. And it has similar geology. And that last point is really what I'm going to be getting at today, talking about what we call terrestrial analogs. So the fundamental idea is that we can use what we know about geology here on Earth to understand Mars and other planets. Which is great because we can't go everywhere on those other planets. We can see things from orbit or we can see things from the rovers, but that doesn't mean it's the same as going out there with a hammer and banging on the rocks and taking them back to the lab and studying them. So what we can do is we can find similar geology on Earth and study it in person and do all of those things and understand that geology as well as we possibly can, and then take what we learn and apply it to other planets. And so analogs are a key part of planetary science. They're really sort of what we hang the whole thing on. It all relies on having Earth as this reference point to understand the geology. So we do research, we also do field training, technology demonstrations, we train astronauts. You can see here on the right a picture from the Apollo era testing out, doing geology in a spacesuit here in Flagstaff. And USGS astrogeology, where I work and where Greg worked, we've been in the analog business since the beginning, basically since we were founded in the Apollo era. We've been using analogs in northern Arizona and around the world to do this sort of work. And so what I'm going to do today is go through and make a bunch of different comparisons between Earth and Mars, and talk about how they're similar and what those features teach us. So how do we read those rocks, and what are they telling us about the processes that are involved? So without further ado, let's get started. And we'll play a little game here where I'll start them off unlabeled, and you can guess which one is Earth. And then we're starting with a really easy one because this one has a road and some buildings. So anyone who has especially live in northern Arizona or visited will recognize on the left meteor crater. And on the right is a similarly sized crater on Mars. And craters are really fundamental to planetary science. They can teach us a lot about the planet. First of all, they tell us the age of the surface. By counting up the number of impacts, we know roughly how often impacts happen, so we can tell how old the surface is. They also tell us about the erosion, because we know what a fresh crater looks like, and we know how they degrade, and so we can see how much the surface has eroded. We can also see the surface properties. What kind of hole did the crater make when it blasted into the surface? How hard or soft are those rocks? Whether the rocks were fractured, you might have noticed if you're very observant that meteor crater is actually a little bit square. That's because there's some fractures running through the bedrock, and the explosion actually went off in a little bit asymmetrical pattern. And as you can see, especially a meteor crater here, you can see layers. So craters provide this window into the layered rocks in which they impact. So we can see sort of a cross section of the rocks. Both planets, Earth and Mars, have volcanism. And so this is, on the left is Mars, if you didn't guess. On the right is Earth, and you can see how similar they look. The scales here are pretty different. On the right, this is Hawaii in Earth, and on the left is actually a nighttime infrared image of Mars, but that allows us to see the difference in the different lava flows that have occurred over time. And lava flows can really tell us a lot. They give us a detailed history of volcanic activity. We can see which flow is on top of which other ones. And we can also measure the flows and study them and figure out how big were the eruptions, how often were they happening. And then if we're either on the surface or if we're using spectroscopy from orbit or from airplanes, in the case of Earth, we can get the composition, what minerals are in the lava. And then if we're on the surface, we can collect samples. And the samples are sort of a holy grail in planetary science, because if you get a volcanic sample, you can use that in the laboratory to tell the exact age, assign a number to how old that rock is. And that can be sort of the keystone to understanding all the geology of the planet. So that's one of the things that Perseverance rover is trying to do, is get a sample of a volcanic rock. This one is a pretty easy one. I won't hold you in suspense here. This one's all labeled. But on the left is the Kilauea volcano on Earth, and on the right is the caldera on the top of Olympus Mons. Drastically different scale here. Olympus Mons is this volcano that's the size of Arizona. And so just the caldera, the hole in the top of it, is like 50 kilometers across, whereas this one on Kilauea is just a couple kilometers across. But you can see the similarities. You can see as the lava erupts out, these big lava chambers collapse, and you get these arcs of fractures.
Person.
I think someone needs to mute there. You get these arcs of fractures and down-dropped different stages. And so these calderas can tell us a lot about the volcano. What is the history of that volcano's activity? How big were the eruptions? A lot of the same things that we get from the lava flows, we can measure and study from the caldera themselves. You also you can see on the left in the Kilauea volcano, there's a little lake there. So there's evidence for water there. In the fact that there's a lake, you can also get explosive eruptions if the lava comes into contact with that water, and that leaves a mark on the volcano. And so that can tell you about whether there's groundwater in the area. This is a little bit of a different view. This is a comparison that I put together the other day in topography. In the images, the Earth image had trees and different roads and stuff that were really obvious and hard sort of obscured the similarity with Mars. But if you look at the topography, these are quite similar. And what you're looking at here is fields of small volcanoes called cinder cones. And so on the right is Earth. This is actually just near Flagstaff, the San Francisco volcanic field. And on Mars, this is a small patch of a very, very large field of cinder cones on Mars. Pretty similar scale as well. And cinder cones, again, it's a similar story here. We see evidence of volcanic activity and get the history by seeing how old these cones are, how eroded they are. They can tell you about the water in the subsurface, because if there's a bunch of water, the explosive eruption is different versus if it's a very dry eruption. And you can figure out the composition of the lava both by measuring it and by the morphology. The shape of the volcano is somewhat determined by the composition of the lava. And likewise, samples of this lava are useful for finding ages. And for those who are Northern Arizona natives or familiar with the area, this will be a familiar site. I'll let you, it's obvious, the one on the left is Earth, and this is SP Mountain or SP Crater, just north of the area shown in the previous slide. But it's sort of the best of both worlds. You have the cinder cone and the big lava flow coming out. And here's a very similar feature on Mars. So just to show that there's a lot of similarities. Mars is a very volcanic planet. And so studying volcanic areas on Earth can really help us understand what we're seeing on Mars. So moving on to a different kind of landform, the windblown sand is quite similar on Mars and Earth as well. So this is one where it is genuinely very difficult to tell the difference. This is basically the same scale image, and they look almost indistinguishable. So I'll give you the answer. On the left is Mars, and on the right is Earth. This is at the Great Sand Dunes National Park or National Monument in Colorado, and this is in Meridiani on Mars. And so these little ripples, these are not dunes, these are very small. These are only a few inches tall and a few meters across. But this is what forms when you have wind blowing sand and gravel, sort of coarser grain stuff that doesn't really go flying in the wind. It just gets sort of nudged along. And these can tell you the modern or the semi-modern. We think the ones on Mars actually are quite old. We've found some that have impact craters in them. And so they're not many millions of years old, but they're quite old in some cases. But they do tell you the direction of the wind, because you can see which way it was pushing the sand. They also tell you the amount of cementation, how stuck together are those little grains. And that tells you the amount of water involved. You know, water tends to be necessary to cement these things together by dissolving salts and then depositing them in between the grains. And so on Mars, we'll drive our rover into these things and scuff them up and see how well they hold together, basically, to figure out how cemented they are. And we can do the same thing on Earth and learn about the history of this little area. And we can go to a larger scale as well. Large sand dunes like these are very similar on both planets as well. And so I'll reveal the answer here. The one on the right is the Earth. The one on the left is Mars. You'll see this is true of many of my comparisons. The Mars pictures are actually a lot crisper, just because the high-res camera is such a beautiful camera. They're black and white, but the basic landforms are very, very clear, and you can see the very clear similarities. There's some differences too. The sand on Mars tends to be black. Like I said, Mars is a very volcanic planet. And so a lot of the sand tends to be volcanic grains as well. And so you get black sand, whereas on Earth you get sand ranging all the way from bright white at White Sands in New Mexico through shades of brown. And we also do have some black sand on Earth as well. But sand dunes can tell us a lot. They tell us the modern wind speeds. This loose sand is moving right now on both planets. So we can see which way the wind is blowing, how hard it's blowing, and how much it's moving, how much sand it's moving each year. We actually have locations on Mars where we've taken a picture of the same area year after year from orbit, and we can actually see the sand dunes moving forward. And likewise, similar to the smaller features, the large sand dunes, we can see how much cementation there is, how much water there is. Sand dunes also clue us in that there's a source of sediment, that something in the general area is eroding into sand. And they're also great targets for studying the composition. They tend to be really clean. On Mars, one of the things we struggle with is everything gets covered in dust, but sand dunes are self-cleaning. They eat those little pieces of sand blowing in the wind, tend to scatter the dust away, and you're left with nice clean sand, which is a great target for looking at with spectroscopy and telling what that sand is made of, and therefore what are those rocks made of that are sourcing the sand. And this is a great comparison. This picture on the right, I think this one's pretty obvious since the left is an aerial photo from an airplane. The one on the right is Mars. This is a very famous picture of Mars. It's such a bizarre and beautiful example of sand dunes where you can see it's almost like they're dripping off of this mesa and blowing to the left. And you know, putting together this talk, I came across this picture of Earth, and I had never seen the same thing happening on Earth, but here it is. You have a big pile of sand with these long linear dunes, and then these small little what are called Barken dunes breaking off and sort of dripping away from the main mass of sand. And so just another very dramatic and sort of aesthetically pleasing comparison between the dunes on Earth and Mars. I did want to say, though, it's not all the same. And this is a discovery from a few years ago from the Curiosity rover, that the sand dunes on Mars are a little different. And this picture illustrates it really beautifully, as well as being just a really nice picture. Dunes on Earth, you have the big sand dune, and then you have the really small ripples, but they don't have what you see here in the picture, which is these sort of 1 to 2 meter scalloped ripples on the surface of the dune. These are due to the thin atmosphere on Mars, and they are not seen on Earth dunes in air. We do see them sometimes in dunes that are under moving water on Earth. So sometimes the analog is not quite as obvious as you think. In this case, the analogous process on Earth is actually happening in certain streams and rivers rather than in deserts. But it's the same basic physics, where these things are formed by the sand grain not getting blown up into the air and what's called saltating. Rather, it's sort of being dragged along the surface. And so it's just this quirk of the atmosphere on Mars where you get this intermediate size of ripple on the dunes. And so this was an interesting case where our analogs might lead us a little bit astray until we find the correct, less obvious analog. So this is an interesting type of feature. These are called Yardangs, and Yardangs are long ridges of rock that are eroded by the wind. And so I will reveal that the one on the left is Earth, the one on the right is Mars. But you can see they look quite similar. And these Yardangs tell us the past and present wind directions. You can see, obviously, the wind in these pictures was going upper left to lower right, or vice versa. And if you study the Yardangs carefully, you can tell which of those it is. They tend to be blunter on the leading end and more tapered on the downwind end. They tell you that there's a bunch of erosion happening, that the rocks are very soft. You don't tend to get this in really hard rocks, because really hard rocks stand up to the sand blowing in the wind a lot better. And as you can see, especially in this picture from Earth over here, the Yardangs also are great at exposing layers in these soft rocks. And we see that on Mars as well in some cases. So the next slide, this is an example of Yardangs in Gale Crater, where the rover is exploring. This is up the mountain a little bit from where the rover has reached so far. But this is a really classic example on Mars of Yardangs. And we actually have two different geologic units. On the left is a lower down unit that's darker. On the right is a younger unit that's brighter. And you may ask, how do I know that it's younger? Well, it's overlapping this crater. So this older unit is old enough that it has some pretty large craters. This is several hundred meters across. And then this white stuff is on top of the crater. So this was deposited and has now eroded back and is revealing this crater underneath. And both of these units have been eroded by the wind to form these Yardangs, so recording the direction of the wind that has eroded them. And so this is just another example. And if you squint, you can see that, you know, all the rocks here in Gale Crater are very, very highly layered, just like the Yardangs on Earth in the previous slide. We can also compare pictures from the surface taken by the rover or taken by people. And so this is an example where I think the comparison is pretty obvious. There's not too many jet contrails on Mars. But you can see here that the top picture is Mars. This is a stretched color version. The sky on Mars is not this blue. It's sort of an exaggerated color stretch just to highlight the differences that we see. This is again at Gale Crater. And down here, Arizona natives should recognize this. This is a picture I took in Sedona, but it's a strikingly similar landscape. You see these hills and mesas of layered rocks, just like we see in Sedona, changes in the color of the rocks, indicating changes in the environment in which they were deposited. So, you know, this is part of why we went to Gale Crater on Mars, because sedimentary rocks can tell us about how conditions change over time. I like to say when I'm talking to kids at school talks, each layer is a change in environment. And so something has changed. Even if it's still sandstone above and below, something has changed. The grain size has changed, something has changed. And so by studying layers in rocks, we can study changes in the environment, changes in the source of the sediment. Are we getting sand from the east rather than the west, or switching from sand to mud? And we can see the amount of water. We can see the transition from sand dunes to lake deposits to ocean deposits and back. We also get to see what happened after the sediment was deposited, both immediately after it was deposited. So when it's still soft, you can get deformation and interesting things revealing what has happened to those rocks. And then much later, after these rocks have turned into rocks and solidified, you can get fractures and water going up through those fractures and depositing new minerals. You can get faulting, big earthquakes shifting the rocks around. And all of that puts together a picture of the history of those rocks. And so geologists love these big stacks of layered rocks, and they're super fascinating. They also tell you about erosion. Especially whenever I go to Sedona, but anywhere on the Colorado Plateau, when you look at the geology, you have to remember what isn't there. All of Sedona essentially is the town is in the area that has been removed, where all the rocks have been removed, and what's remaining are these buttes that make the spectacular scenery, but a lot has been taken away. And the same thing is true at Gale Crater, where we have this giant mountain of layered rocks in the middle of the crater, but that mountain doesn't reach to the edge of the crater. It's been eroded back so that we can see the layers. And so it tells us that some pretty significant erosion has been happening over a very long period of time. Here's another nice view from the ground of what's called crossbedding. And I'll reveal the answer if you're looking carefully. I put in grayscale just to hide it a little bit, but you can see there's some plants on the Earth one, not too many bushes on the outcrop on Mars, but you can see the similarities right away. These tilted beds are what's called crossbedding, and this is essentially petrified sand dunes. Sand dunes formed by sand blowing up to the top of the dune and then avalanching down the far side, and it forms these repeated tilted layers. And you can actually learn a whole lot about the environment by studying these layers. You can tell, that they're sand dunes, that they're not a lake deposit or an ocean deposit or a volcanic deposit or something. And so that tells you that it was a climate where you would have a sand dune. You can also do cool things like tell what direction the wind was blowing millions, or in the case of Mars, billions of years ago. Which way was the wind blowing? You can figure that out by measuring the angle of these layers. And you can also look at the history of the erosion and the deposition. If I go back, these places where the tilted layers are chopped off by the flat layers, that's a place where the sand deposited for a while, and then there was a period of erosion where it just sliced off the top, and then another period of deposition. And so you can put that together and figure out a story of how often were these dunes going by, how much were they piling up on each other versus eroding down into each other. And again, just like the stacks of sedimentary rocks that I talked about on a larger scale, you get the history of the activity after the dunes were petrified as well, with fractures and alteration, chemistry happening in the rocks after the sand dunes were in place. So this is a picture from some work that I did a few years ago. And this is what those same sorts of cross-bedded layers look like if you're looking down from orbit rather than on a small scale outcrop. So these are much larger, hundreds of meters, but on the left is Gale Crater on Mars, and on the right is White Sands, New Mexico. Heavily stretched, so you can actually see the patterns, but this is an area with no dunes right now, but it's an area where dunes were before, and they've left these cross-bedded layers, and then they've been planed off, exposing this nice surface. And the comparison is pretty clear. You get these sort of sinuous patterns where they're chopping each other off. And so we see that this is up near the top of the mountain in Gale Crater, very, very high in that stack of sedimentary rocks. And this is in White Sands, New Mexico. So we see it at both the small outcrop scale. We even see it much smaller than the outcrop that I showed you on the centimeter scale. We see little tiny cross beds as well, all the way up to these giant ones. And then again, this is another obvious one because it has bushes, but I loved this picture from the Mojave Desert because it's so similar to this picture from Mars that we took when we were studying this sand dune, looking out at the crater rim. Whenever I see our rover pictures of the crater rim, I'm always reminded of Mojave. I drive back and forth between Flagstaff and California for rover related stuff pretty frequently, at least before COVID I did. And every time I'm crossing that desert, I look out and I think this looks just like Mars if you take away the bushes and the trains and things. And so I just wanted to include this, not because I have a real profound geologic interpretation of this picture, other than to say that these are both really dry climates where you have a big basin and you have a source of sediment that's making sand dunes, and you have erosion in a dry climate, and it forms these very similar landscapes. Here's another example, again, a pretty obvious one with telephone poles and trains and roads, but this is the scene that you see driving across the Mojave, and this is the scene that you see driving across Mars. And basically all that Mars is missing is a highway and a railroad track going down across the floor of Gale Crater, and they look basically the same. And of course, there's flowing water as well. So on the left is a picture of the Atacama Desert in Earth, a very, very dry place on Earth, but still crisscrossed by these river channels. On the right is Mars, a Viking image where we can see evidence that water was flowing. And of course, this tells us that there's flowing water. Also, if you measure these carefully and study them carefully, you can figure out how much water there was. How long ago was it? Do you have a bunch of craters on your river valleys or not? And you can also tell whether the water is running on the surface or whether it was flowing underground and undermining the surface and doing what's called sapping. Speaking of the Mojave, we see this in the Mojave and in deserts on Earth. This one on Earth is in China, but pretty much any desert you see what's called alluvial fans, where you have water flowing from some mountains and then depositing piles of gravel and sand in a dry basin, forming these fans. So these are ones that I've studied on Mars, and this is a much, much larger one on Earth, but it's the same basic process. And again, they tell you that there was flowing water, that it flowed into a dry basin, and you can study how often the water flowed, how long ago, how much erosion is there, how much has the mountain area been eroded to form this fan. Another feature that we see in deserts on Earth as well as Mars is these inverted channels. So this is what happens when you have flowing water and the riverbed is more resistant to erosion than the surrounding land. And so when things dry up and you start to have more erosion, the surrounding land gets eroded away, but the riverbed is resistant, so it forms this raised ridge. And so again, it tells you that there was flowing water. You can measure them to figure out how much there was, what sort of flow, whether it was a big muddy, more like an avalanche, or a meandering stream like we have here with these tight curves. And obviously it tells you that there's erosion because this river once was a valley and now it's a ridge. and that it tells you that something made that riverbed harder. Often it's just the fact that you have larger rocks on the bed of the river than elsewhere, but sometimes it could mean that there was lava that flowed down that river channel, or that there was certain chemistry that made it cement really hard in the river channel compared to the surroundings. And another thing, sort of the giant version of that, is the preservation of deltas on Mars. So on the left, of course, is Earth. You can see the crop land and the false color highlighting all the plants. On the right is Mars, where you have not an inverted river channel, but an entire inverted delta. And a delta is what happens when you have water flowing that, instead of encountering a dry basin, like an alluvial fan, it encounters standing water. So that's a big deal. That tells us that there was a lake or even an ocean. And you can figure out how long the water was flowing, how much erosion has occurred. You know, on Mars, we can see the toe of the delta, but we can see that it has been eroded back. But deltas, importantly, also tell us where to look for biomarkers. Deltas are really good at sorting out, and farther out on the delta you go, the finer the sediment is, the more muddy and silty it is. And that's where the sediment tends to capture microorganisms that are living in the water and traps them in the rocks. So that is why the Eberswald Delta was chosen as the landing site for the Perseverance rover, because if we go to a delta, we know where to look. We look for those rocks that were deposited at the bottom of the delta, and that tells us the rocks that are most likely to have evidence of life. So here's what the delta where Perseverance landed looks like. You can see the river flowing in here, and this is the delta. We think it was once more extensive. We see these little patches of delta-like material out farther in the crater. So we think erosion has sort of eaten into it, and this is what's left. But it's still this beautifully preserved example of a delta. And the next slide is going to take a look at this little butte as seen by the rover, to show you why we are pretty sure it's part of a delta. On the top is the picture from the rover, heavily stretched, so the rocks are not actually blue and these are not actually that red. It's just to highlight the differences, but you can see these tilted layers on the picture from the rover. And here's a couple examples from Earth of the exact same thing, where the front of the delta is where the sediment is sort of cascading down into the lake basin and forms these tilted layers, sort of like what we get with sand dunes, but much larger and sort of a different geometry. And so finding these is sort of our smoking gun to say, yes, this is part of a delta. Here's another picture from Jezero crater. Again, a pretty obvious comparison, since the one on Earth has water in the river. And I'll also mention the one on Earth is hugely larger than the ones we see on Mars, at least in this example. But these are what's called point bar deposits. These curved, sort of crisscrossing deposits are what you get when you have a meandering river, like this one in Russia, and it's meandering back and forth. And as it goes back and forth, it deposits layers of sediment in the loops of the river, and then the river changes course and it goes a different way, and it cuts into those layers and deposits a new set. So we see them here on the delta in Jezero, and these can allow us to put together a really, really detailed picture of what the water was doing, how fast did it flow, how often did it flow, how long did it flow. It can tell you a lot about the history of water in that area. And so we're really looking forward to getting up on the delta in Jezero and doing this sort of study with these layers. There's also the similarity in features related to ice. So on the left here is Earth, a nice big glacier coming down to the ocean. Obviously, the one on Mars is not going into an ocean, but it's pretty similar. It's a bit smaller, but you can see that sort of lobate flowing shape to it that tells us that there is a bunch of ice and that it is flowing downhill. There's enough ice that it's overcoming its own sort of strength and it's oozing downhill. And of course, wherever you have a bunch of ice, you can tell the history of the climate. And especially on Mars, that gives us clues to things like past orbital changes, where when Mars's tilt changes, it drastically changes where ice can be on the planet. And so you get these remnants of previous ages where the planet was tilted and ice was in very different places, where now you wouldn't really expect to find ice, but some of it has remained trapped under rock and dust and sort of insulated So you get these fossil deltas or fossil glaciers. And again, it tells you the erosional history. It tells you that in this area, there was flowing ice scouring the landscape. And so you expect to see the classic U-shaped valleys and all the sorts of erosion that goes with glaciers. Another ice-related feature that we see on both planets is patterned ground. So on the left is Mars, on the right is Earth. Again, the scales are a little bit off, but it's the same basic process where patterned ground, it happens when you have freeze and thaw with ice in the subsurface, and it forms these polygons, and in some cases polygons within polygons, and sort of a fractal pattern. And so again, this gets at the climate history. It tells you that there was ice under the surface, there still is ice under the surface, and that it has affected the shape of the surface by freezing and thawing. But of course, there are differences. Ours is not Earth, and we always have to be careful. And so this is an example of something on Mars for which there is no Earth analog. And I will get you a little bit oriented because I love this picture. It's an optical illusion. The flat parts are high. The ridgy parts are low. So this is a high mesa. This is a low basin. The light is coming from the lower right. And this is what we see on the south polar cap of Mars, where we have a layer of carbon dioxide ice that is sublimating away. You don't get that on Earth. It's not cold enough. And so you get weird geology when conditions are so unlike Earth, there's no analog. And so we always have to keep that in mind. We don't always have a good analog, but often we do. And when we don't, that really tells us something. That tells us that we're looking at something very, very different. So I'll conclude there. I think the sort of take-home point is that we understand the geology of other planets by comparing with the geology of Earth. They go hand in hand. We have to have that example, or else it's very, very difficult to understand what's going on other planets. Like that Swiss cheese terrain I just showed you, if you don't have the example on Earth, then you have to turn to the laboratory or to simulations to figure it out, and that can be a lot more challenging. Mars and Earth have a lot of geology in common. The scale might be very different, but often it's common enough that we can learn a lot. Sometimes they're similar but not identical, like in the case of those dunes where we had to go searching a little bit for the correct analog. And sometimes there is no natural analog when things get really extreme. And then the final point I'll say is that Northern Arizona is full of analogs. We've been using the analogs around here for research and training and education and testing for many, many years. And we have a new sort of renewed effort to develop terrestrial analogs, collect data about them. And I'll just include this one link here to a recent field guide that we put out. It's an online interactive field guide for SP Mountain, that volcano with the lava flow that I showed earlier. And so we're working on similar things for other analogs in the area. And so this is an ongoing program, and we're excited to sort of get back to our roots and do more with analogs in the coming years. So I will stop there.
That's awesome, Ryan. Thank you. Excellent. Really interesting stuff. We have a bunch of questions, and I don't know if we'll have time to get to them all. So if it's all right, I'll just go ahead and ask the first one that came in that has a bunch of tabs. What was our estimate of what Mars geology was like before we sent any rovers or landers? How well did reality match our estimates once we started collecting data from recent missions? And a follow-up to that is, do you think the same will hold for, say, something like Europa? Like, how confident are we in what is on the surface of Europa, close to what we expect it to be?
That's a really good question. So in the early days of exploring Mars, it was a smudgy picture in a telescope. And so when the first Mariner probes got to Mars, it was really unknown about what we were going to see. Some people thought that the light and dark patterns on Mars that changed with the seasons were like vegetation. So when Mariner took its first pictures and revealed a bunch of craters, everyone said, oh my gosh, it's just like the moon. We were all wrong. There's no life there at all. But then later on, Viking came and took those pictures of the river channels, and it sort of pendulumed from it's just like the moon to, okay, it's not as like the moon as we thought. And then for a while, it was sort of thought to be mostly moon-like with a little bit of flowing water. But in the last couple decades, we've started to send higher resolution cameras where we actually can see the layered rocks. And so discovering that there's sedimentary rocks on Mars was sort of a big leap forward, where all of a sudden it was saying, okay, this is not just pulverized regolith like we have on the moon. There's something more going on here. There's more geology going on, more complicated history of erosion and deposition. And so sort of from there, it's been a matter of refinement, getting better and better pictures, better and better understanding. But yeah, early on, the expectations were kind of wide open, and we narrowed way down. I think for Europa, we have better pictures. I mean, not great pictures, but better than a fuzzy telescope picture. So we have the Galileo and the Voyager images of Europa. So we have a pretty good idea. Of course, as we get more detail, we'll see surprising things and things that we don't understand. But I think we have a better idea of Europa now than we did at the beginning of exploring Mars.
Cool.
Wonderful, thank you. We have another question here that says, I'm puzzled. How can one get so much information just from images? Say you have an image taken from a rover. Can you tell things about rock, soil, say if two different rocks are similar material, just by looking at the shape, color, and texture of the two rocks in the image?
You can. You can learn a whole lot about a rock just by those factors. You know, how does it break? How does it erode in the wind? You know, and what color is it? Color is not a definitive guide, but it sure is a clue. That said, there's still a lot that is hard to say. You know, one of the things we're struggling with the Perseverance rover right now, and we struggled with Curiosity as well, is you find a rock on the surface. Is that rock volcanic or sedimentary? Because we can measure the composition and it'll have a volcanic composition, but you can have a sedimentary rock made out of sediment from a volcano. And so it can actually be way harder than you would think to answer that question. And you know, we're still refining it, and you know, you use your best cameras and you zoom in really close and you know, try to put the rock into the greater context to figure it out. So it's sort of both ways. Yes, you can learn a lot about a rock, but at the same time, there are some pretty fundamental questions that can be surprisingly tricky to answer, because, you know, if all your sediment is volcanic, you can sort of be tricked into thinking it's one or the other. And so we have to be pretty careful about our interpretations.
You also have spectroscopy where you can determine some compositional information, right?
That's right. So spectroscopy gives you sort of your next level, but even that can be tricky if your sediment is the same composition as your original volcanic rock.
Okay. Couple of related questions. One is, does Mars still have ice now? And the other question is, would CO2 ice form the same landforms as water ice?
Both good questions. So Mars does still have ice. A few years ago, the Phoenix mission landed in the Arctic of Mars, and its mission was to discover ice under the surface. And it accomplished its mission the moment it landed, because its rockets blew away the soil on the surface, and about 6 inches below the surface, there was solid ice. And so there's ice buried under the surface, and there's ice in the ice caps, and there's ice in those fossilized glaciers that I showed. There's areas where that ice has been preserved. As far as the CO2, it forms very, very different landforms, because CO2 doesn't turn to a liquid. It goes straight to gas. So you get that weird Swiss cheese terrain that's just bizarre looking. And you also get interesting stuff happening where you have a seasonal layer of CO2 where it deposits a layer, and then in the spring it starts to warm up, and it actually heats the ground under the ice before it heats the ice. And so you have geysers of CO2 vapor coming up through the ice and bringing sediment and forming weird, what are called spiders, like these very sort of dendritic sort of fans and streaks of stuff blowing in the wind as that ice sublimates and goes into the atmosphere. So it's very, very different from what you get with water, where it melts in water ice, which melts into water, and you have flowing stuff. CO2 does its own weird stuff.
And I'm going to try to combine two questions as well, just for time, because we're almost out. One person's wondering how high the inverted riverbeds are, bed hills are, and another is wondering how long ago there was water flowing on Mars.
Okay, so the inverted channels, they're usually not like towering, you know, a handful to tens of meters, probably at the maximum. So they're not like a giant fin. They're more of a small rise that follows the shape of the river. If they got too sort of tall and narrow, they would be very easy to erode and they'd fall down. And then when was the most recent water flowing? It's a tricky question. There's some features that are relatively recent, even active now, that some people think are water. These things called recurrent slope lineae, but there's a lot of evidence piling up that shows that those may actually just be dust doing interesting things. And likewise, there's gullies that we think formed relatively recently, but other people are saying that maybe those are mostly dry. So to get back to something that's definitely flowing water, you probably have to go back hundreds of millions of years, if not a billion. But if you want stuff that is maybe sort of related to water, we're not sure. There's some candidates that are much more recent, if that's your criterion.
Wonderful. Thank you for squeezing both those in there in the end. I apologize for any questions we did not get to tonight. We have to make sure we set up for the next presentation. Ryan, thank you so much. This was a wonderful talk. Comments in the chat have folks searching, how can I watch this again? Reminder, scifest.org is our website. You can find links to the survey, which I also put in the chat. Also, our Festival of Science YouTube page, where you'll find all recordings. Thank you so much to everyone out there for your support, and especially Ryan for being here tonight. And we'll see everyone at our next talk at 5 o'clock. Reminder, you'll have a separate link for that one. So we're going to close out this and we'll see you next. Thank you.